Hello, this is a 15-minute introduction to open source video processing pipelines. It's a huge topic and there's a lot more information on the wiki. So if you scan the QR code, that'll take you to the wiki. You can click on contact if you have any questions for me. This is based on an article that I'm presenting in November 2025 at the Open Source Hardware Conference in Chemnitz, Germany. But really, you want to go to wiki.pythonlinks.info, search for whatever you need, and you'll find some interesting stuff. The professionals in this field really like it. Joshua said it looks nice, organized a bit like a series of chests in a gold mine. There's just tremendous amount of really great content in there. Took months of research to find it all. So here's a project I'm working on, a drone video pipeline. There are many different steps in the pipeline, and like many of these projects, some pieces are closed source, some people are open source. For example, MIPI, everybody talks about MIPI, but to even read the spec, you need to pay money. It's a proprietary spec. When we think about cameras, historically, you could think of the Canon camera on the left. More recently, we have these amazing multiple image sensors integrated into a single video, different focal ranges, different exposure times, rangefinders. Just amazing what they do with these cameras on cell phones. But typically, the engineers think more about Raspberry Pi cameras. So $50, you get a 12 megapixel camera. And then for another $10 or $15, you have these Raspberry Pi Zero boards, and they've got the MIPI interface, and they have DVI HDMI output, and USB and compression. Just amazing functionality for very little money in all of these devices. They all start with a lens. You may have studied lenses in high school or college. But if you take a look at the recent Apple patents, they've just gotten way more complex. And it's the same thing in every single stage of these pipelines. They started off simple. Everybody optimizes their piece of the pipeline, and the whole thing becomes incredibly complex. Just take a look at the image sensors. There are 874 image sensors listed in one database. And in my experience, it turns out that there are actually a number of vendors they don't even list. What do we do with these image sensors? Well, often we assemble them into a camera stack. Here's the ArduCam USB shield. At the top is a lens. Beneath that is the image sensor. The bottom board is a USB 2 or USB 3 board. There's so many different protocols. They have these adapter boards that connect the various sensors on the top board to the USB on the bottom board. ReCamera is another interesting camera stack. This one's completely open source. It's all metal, very nice. It has to be metal because the middle of the camera stack is typically a RISC-V or some kind of microcontroller that gets very hot. But it looks nice when it's all assembled. What do we do with these camera stacks? Well, video cropping is one thing. Video cropping is really easy on the desktop because you just have a video of a new size. But when you're doing this in many video processing pipelines, you need to scale the image and get all the timing correctly. So that gets a bit difficult. Defective pixel correction happens. If you have short circuits, then on a black background they'll show up as white pixels. If you have open circuits, then on a white background they'll show up as black pixels. We can do pixel binning. My desktop display is only 1.4 megapixels, but these Raspberry Pi cameras 12 megapixels. What do you do with all those extra pixels? Well, you can do averaging. So you average several together and you get less noise. That's a good thing. Historically, they had much smaller image sensors compared to the display, and so what they did is they took on the background you have the actual image sensor, and then they have filters for various colors on top. And then what the Bayer filter would do is would take any point which was a single color and merge that with neighboring to create as many pixels as you had image sensors. Now you've got way more points than you need, and so it makes sense just to take four points and turn them into a pixel, shrink your image size down by a quarter. We also have to look at the spectral response of each of the data points for each of the colors. So the camera has a spectral response, the display has a spectral response, your eyeball has a spectral response. They're all different. So if you look at this woman's face on the left-hand side, the colors are off. She looks like a zombie. And that's because humans are very sensitive to colors of faces for evolutionary reasons. We don't really care about the colors of the trees. And so what you have to do is you have to rotate the colors in order for it to look normal to the human eye. If you have a fisheye lens, which are very inexpensive, you can do fisheye dewarping, as in this image, very computational intensive. For that, you really need something like an FPGA we'll get to in a minute. Another open source solution is the completely open source, but it's only for one piece of the pipeline, is the RunCam Wi-Fi version 2. So it takes a DVI HDMI signal out of a camera, and then it transmits that over Wi-Fi. What it doesn't do error checking, and because error checking introduces a lot of delay, and so it just assumes the pixels went through successfully, and so it's much faster. Completely open source, the case, the board, the software, the firmware, I should say. Blade RF is another such example, but this actually uses an Xilinx FPGA, also completely open source. Often the last step in an image processing pipeline is like a DVI output, but we really want USB on so that we can do demos over the internet, record videos. And so there are these less than $10, you get these DVI USB 3 dongles, which do the conversion. Very nice. If you look on the inside of those, they have an MS2130 chip. They have a double frame buffer, also very common in image processing pipelines. The HDMI DVI signal comes in, it writes to one frame buffer while the USB 3 is reading from the other, and at the end of the screenshot, at the end of the image, they switch. If you can get a shrink wrap solution, if you need to do something custom and the bandwidth is low, you can use libmpx on microcontrollers. The problem with microcontrollers don't have much memory, and so they don't have doing double frame buffer is really very difficult. And so what these guys do is they do a ring buffer, and so the data is written to one end of the ring buffer, it's read from the other end of the ring buffer, and in between pixel reads and writes, you can do various operations on the data. And in particular, they're now moving to a single instruction multiple data, so then they can do multiple things on the ring buffer at the same time. Really interesting software. I really like the guy who's doing this. Tremendously knowledgeable. But really for video processing, for anything higher, you need an FPGA. Ideally, it's good to use an open source FPGA. When we say open source FPGA, we don't mean that the chip is open source. We mean that the synthesis tools are open source. So typically Yosis and NextPNR support. This whole ecosystem runs very fast, evolving very, very rapidly, hugely interesting. And a rapidly increasing number of boards are being supported by it. If you want a MIPI interface, then the Lattice NX17 and 40 are open source and have hardcore MIPI blocks up to 2.5 gigabits per second. This 33 is closed source. On my desk I have the 54 European Olimex GateMate board. This doesn't have MIPI, but I can use DVP camera, the Waveshare OB5640, fisheye lens 1660, a lot more expensive if you want to do the rectilinear lens. And this will do 1.8 volts, so I can connect it into the GateMate board. Here's a zoomed in view. In January, the IcePi Zero is coming out, and that has the Raspberry Pi form factor, so you can just plug a Raspberry Pi Zero into that. That's got a MIPI hardcore and do the transfer between the two. Of course, these parallel interfaces are limited to like 90 or 100 megahertz, and so that'll give you 1.5 gigabits per second at 60 frames per second. So that's using this Raspberry Pi Zero for $10 or $15 as the bridge. An interesting, completely open source video processing pipeline is on the frame glasses. They have a camera, they have a FPGA, they have a display on the camera, and they also have a Bluetooth microcontroller to talk to some AI back end. So the image comes in, it gets processed by the FPGA, it goes off to the MCU, and then it goes off to the cloud and comes back down and gets displayed on the OLED display. I won't talk much about the frame display, but let's focus in on the camera pipeline. So on the left-hand side, you have a camera that comes into MIPI DPHY, that gets turned into pixels, it gets debayered, it gets cropped, it gets compressed using a JPEG encoder, and then that gets stored in a large RAM and eventually over SPI sent off to the microcontroller, which speaks to the cloud, gets the AI recognition of image, and sends the results back down to the microcontroller. There are a ton of different display interfaces to choose from, some more open than others. But let's take a look at a complete system. Here we have the DJI multispectral cameras. They're often used for looking at farms, fields, to see how strong the photosynthesis. Photosynthesis is a very good mark of the health of a plant. So here you have the photosynthesis spectrum. And here you have the DJI nominal frequencies that they measure. As you can see, it's not aligned with the photosynthesis spectrum. Because of climate change, rising food prices, if we could do something to help the farmers, that would be really good. The world really needs like an open source camera where the lenses, where the image sensors are tuned to the photosynthesis spectrum, application specific. You have similar issues with firefighters, and also with search and rescue teams need application specific cameras, multispectral cameras. Okay, so there's a whole section on recommendations. Basic thing is, if you find a shrink wrap solution that does what you need, use it. That's the easiest. If you need to do something custom for low bandwidth, go with Zephyr OS on a microcontroller, particularly once they get single instruction, multiple data working. Open source, go with the Lattice NX. That'll take you up to 2.5 gigabits per second. If you need more, you have to go with the closed source FPGA. If you want a European made FPGA, then try GateMate. If you're using one of these open source without a MIPI hardcore, then use a Raspberry Pi MIPI to DVP bridge, also all documented on the wiki. For longer cables, the trucking and car industry often has a camera in the back or a LiDAR sensor and displays in the front, so they need longer cables. There's a whole discussion about what to do there. As always, lots of different protocols to choose from. Any questions? Here's a QR code for the wiki. Click on contact if you want to contact me. Don't be shy about asking questions. Everyone else probably has the same questions as you do. Thank you so much.